So your atomic structure and atomic mass, this is one of the points they talk about. They want you to talk about the basic structure, but they also want you to talk about how do I calculate the relative atomic mass? And you might say to me, what the heck does it mean by relative atomic mass? Why can't I just say atomic mass? Really good point. Relative atomic mass is because of this phenomena called isotopes. Now think of it like, I don't even know how to think about it. Just think about it like atoms. What is the best way to think about it? Let's talk about carbon for our main one. So carbon has 6 protons and 6 neutrons normally. So carbon is carbon. It's the 6th molecule on your periodic table. Being the 6th molecule on your periodic table, something I should have discussed before, each of these molecules have their number, their atomic number, this atomic here, their atomic number refers to the number of protons they have. So this has 3 protons, this has 4 protons, this has 5 protons, carbon has 6 protons. Now we learnt back on this last slide that the relative atomic mass of carbon is 12.011. Now you might say to me, how the heck do I have 12.011? It's like, you're counting protons and neutrons, you're going to get a whole number. It's just like, you ask someone how many pets they have in their house, and they say 2.5. You're like, what do you mean by a half? And they're like, well, I've got a fish. It doesn't count. You have 3 pets. You don't have 2.5. So you can't have an odd or a decimal number of protons and neutrons. So then you say to me, well, how the heck did I get 12.011? Well, it's because it's relative, and relative refers to isotopes. So isotopes are essentially atoms of the same element that have a different atomic masses. So carbon, there is so much carbon in the world. You'd have bazillions, you have trillions of carbon atoms just in you yourself. Outside of that, there are unfathomable numbers of carbon atoms around the world. Unfathomable. You cannot even just consider the number. There are so many. So given that idea, not every single carbon is going to have the exact same number of neutrons. It just isn't possible. Yes, every single carbon has the same number of protons because if it had 13 protons, it's not carbon. That's a really, really important fact. You might say to me, well, what about the proton? Well, then a carbon might have a different number of protons. Well, then it's no longer carbon. It's a different atom. The atom is dependent on the protons. Really, really important. But nonetheless, every single one is going to have, they're going to have different numbers of neutrons. So what we like to think with carbon is as a generalization, we've sort of taken massive quantities of carbon and we've figured out generally what are the percentages of each. We don't know exactly, but we know to a pretty high degree what there are. And we know that about 99% of carbon is carbon-12. It has 6 protons, it has 6 neutrons. We also know that about 0.8% of carbons are carbon-13. So they have 6 protons and they have 2 neutrons, and they have 7 neutrons. And we know very, very small number, it's like 0.1 or 0.2% of all carbons are carbon-14, but they have 6 protons and 8 neutrons. So when you make that a relative atomic mass and you do the maths as to what is the average over the 3, your average is 12.011. That's why a lot of people will just refer to carbon as 12. Their atomic mass is just 12. They'll simplify it down. But if you want to be really nitty-gritty, you get a relative atomic mass of about 12.001, which is really, really very close to 12 because most of them are 12. So that's because of isotopes. So isotopes are those different variations. Radioisotopes are isotopes that are unstable and decay radioactively. Carbon-13 and 14 are examples of that. They're not very stable, and that's why there's low percentages of them. So as we said, they're different forms of atoms of an element with the same number of protons and electrons but different number of neutrons. Isotopes have the same chemical properties because they have the same number of electrons but different physical properties due to the different number of neutrons. You can then be stable or unstable. So stable isotopes do not undergo radioactive decay, so it doesn't emit radiation, but unstable isotopes do go under radioactive decay and they will emit radiation. So it's one of those aspects you do need to know about the difference between the two. Isotopes, essentially atoms of the same element, as you can see there. This is what I was talking about earlier. You've got your carbon-12, carbon-13, carbon-14, and if you look at your protons and neutrons, your protons 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, neutrons 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. exactly what I was trying to talk about, and that is why these are isotopes. So different isotopes are found at varying amounts. As you can see here, these are the exact percentages I was looking for, the ones that I was more likely to do. But as you can see, that we assume that about 98.9%, wasn't 99%, but close to, of carbon is 12, whilst 1.11% of it is carbon-13. And then, as I said here, carbon-14, such a small percentage. I thought it was like 0.1, but maybe it's way, 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 way less, is because it just doesn't exist. It's very unstable. So as you can see here, isotopic elements, you write the element, you write the mass number, you write the atomic number here. So you will write your elements a bit differently for this. So you'll write, carbon-13, 6. Carbon-13, 6, carbon-14, 6, carbon-12, 6. So each of your isotopes, you need to be able to write them out differently. So as you can see here, carbon-14 is a radioisotope. As I said here, that's an example of it. You already know what radioisotopes are. I've discussed a bit. Now, there's also decay. This is one thing that slightly alters from VCE to HSC, but I have been through this before at a university level, so it should be pretty fine. Essentially, you have alpha, beta, and gamma decay. Now, gamma decay is the one that's really, really harmful. It's really dangerous to be around gamma decay, gamma radiation a lot. That's things like, I believe if I'm thinking correctly, these are things such as like our nuclear power plants that have melted down. So there's one in Japan, and you have like Chernobyl is another example. They emit gamma radiation. Now, that's why we've built big concrete things around them. They also do produce a bit of alpha and beta. The concrete kind of gets rid of the alpha and beta. The gamma radiation, there's not a lot you can do. We sort of lead plate as well as we can, but it's pretty hard to get around. But essentially, alpha decay occurs in isotopes of the heaviest elements to remove mass, i.e. when there's too many nucleons. So what they'll do is they'll remove a neutron, but essentially it's really the heavy elements. They don't really care too much about it, so they get rid of something that's pretty heavy. Being so heavy, they have a really strong ionizing power, but their penetration power is terrible. So if they do hit something, they can do a bit of damage, but they can't penetrate very well. So therefore, you can get a sheet of paper and the neutron's too big to get through. So it's just going to get stopped. Beta, on the other hand, it's an unstable nuclei that contains too many neutrons, and electron is emitted as a beta particle. So essentially what we do is we actually emit electrons instead. So because we have too many neutrons, there's issues with the mass and so forth. They actually emit an electron first. They then sort of move to alpha decay afterwards, and they go, all right, I'm sick and tired of this neutron, and get rid of it. This just emits an electron, as I said. Electrons are a lot smaller, therefore you actually need sort of a metal plate to stop it. So aluminium it's not very dense, but it's dense enough. And that's what's going on there. Whereas gamma radiation is energy. We're not actually emitting anything, we're just emitting energy. And because you're emitting energy, it's really hard to stop. And therefore you need like a really thick plate of lead. Lead has a really high density and a really high ability to absorb energy, but you still need it really thick. So essentially what it is, it looks like this. So that's gamma. And essentially gamma is just really high level energy. It's got really high penetrating power. It just has low ionizing power to really high penetrating power. It's what makes you very sick. You experience a lot of this. It's really unhealthy. You don't want this to occur, and therefore that's why it's really dangerous. So as you can see here with alpha decay, as you can see here, alpha decay causes the atomic number to decrease by 2. So you go A4 to Z2. And the mass number to decrease by 4. So alpha particle is the equivalent to a helium nucleus. Beta, on the other hand, occurs when there is an excess neutron. So a neutron decomposes into a proton and an electron. Essentially, the atomic mass increases by 1. And then gamma radiation particles are released. Gamma particles are released when the atom has too much energy. Due to being energy, there is no change in the atomic mass or number. So, radioisotopes, we've already discussed this. They can be helpful in many real-world situations, such as imaging, historical dating, medical treatments, etc. The reason they're really useful in historical dating is because we understand that they have half-lives. So there's the half-life of a lot of radioisotopes is really long. We're talking tens of thousands of years. After tens of thousands of years, half of the amount of radioisotope you have in a sample, or you expect to have in a sample, should have reacted, should have emitted off its radiation and gone. It should have emitted what it needed to and stabilized itself. So over time, you can take samples and go, all right, well, there's this much. I should have had this much if it was at 100%. Therefore, I can tell it was this old. So that's sort of how you do it. Carbon-14 is a man-made isotope, so it's extremely rare cases where it occurs naturally. Undergoes beta decay, used in carbon dating, so useful for estimating fossil ages. As it says man-made, it's because it comes from fossils, it comes from humans. So it is sort of still occurring naturally, but one of those things. The other one that's really cool is uranium-238. It's a naturally occurring radioisotope. It undergoes alpha decay, and it's used for making nuclear power and generating nuclear power. But the problem is the way that we work with it ends up producing a bit of gamma, and it gets really dangerous.